My name is Lucas Thompson from the University of Southern Mississippi. This is my presentation on undergraduate research in swarm robotics for the Undergraduate Research Apprenticeship Program. Over our first few weeks, we covered several topics that we would need to be familiar with over the coming weeks of research. To start out, we implemented the Markov decision process and Q-learning projects from the University of Berkeley website to get familiar with the basics of the artificial intelligence we would be working with. Next, we saw demonstrations on the robots and simulators we would be working with, along with explanations on how to actually implement code into them. We then spent portions of the next several weeks implementing code and algorithms in the simulators in order to get familiar with how the robots operated. We worked on several projects in order to get familiar with the robots and how they worked. One of the first projects we worked on was making changes to our simulator in order to make it more functional for our research. We added several features such as a debug interface, functionality to pause the simulation, and the ability to load robot positions from a list. We then moved on to actually working with the robot code by implementing several algorithms. The first was a foraging algorithm that had the robot spread out to find a simulated food source, pick up that food, and return it to their simulated nest. The foraging algorithm led to some work on obstacle avoidance to keep the robots from colliding into each other while searching for food. We also implemented the Boyd's algorithm, which is a simulation of flocking behavior such as you would see in a school of fish or a flock of birds. To have a point to begin our research, we implemented two basic policies in order to have a base measurement to compare our future policies to. The first policy was a group reward policy where the robots chose their moves based on a reward. The second policy was an individual observation policy where the robots chose their move based on the robots they were able to detect in their area. The group reward policy was based on a reward of a convex hull. The robots start out gathered together. They then choose their moves and spread out based on which moves would give them the greatest hull area. The observation policy had robots observe the total count of robots in front, left, right, and behind them. Then the robot would move in the direction that had the least density, while there was at least still one robot that it could detect in range to keep it connected. After creation of the previous policies, we began work on a version of a periodic finite state controller policy. Since this policy generation would be very computative, our first step was to port code from our Python simulator to C++ to take advantage of the speed increases. We also needed to write a program to actually load the policies into the robots, as the policies could grow too large to actually do by hand. To initialize this policy, we constructed a policy graph for each agent. Then, using a trajectory of random actions, we sampled the robot's best possible moves using a simulation to construct the initial policy. Once the initial policies have been generated, it is loaded into each robot. Then, the robot simply makes an observation of its environment. It checks the policy to find the matching observation, and it follows that observation link to receive the action it should execute. Future continuing work into this will provide policy improvement algorithms and the ability to loop the end of the generated policy back to the beginning to provide a policy for infinite horizons. Over the course of our research, we read and discussed several papers to try to come up with ideas for implementations. Here is a list of the ones that were read and discussed in depth.